So in this video, I will show you something that I think is pretty insane, which is how you can use AI to help you reverse engineer proprietary CAN bus signals from a car, truck, ship, whatever piece of equipment you have. To do so, I will be using our CANsub.2 CAN bus interface, as well as PythonCAN and a custom Claude Code skill that I built for this purpose. And as you will see from the free practical showcases I go through, this workflow is extremely powerful, and I would actually say this is now our recommended method for all of our end users that are looking to do CAN bus reverse engineering. As always, don't take my word for it. In the description you will find links for the test data I used behind this. The skill is 100% open source, so you can go and try it out after this video, and I will show you exactly how to do it. Why do you need to reverse engineer CAN bus data in the first place? If you're not super familiar with CAN bus, the way it works is essentially that you can record the raw CAN bus frames from a vehicle, a truck, a car, a ship, and the like, using, for example, a CAN bus interface or a CAN bus data logger. But what you get is essentially just a lot of data bytes and CAN IDs, and you will not be able to make any sense of the data unless you are the manufacturer. Only the manufacturer is able to say how to go from the raw CAN bus data into what we call physical values, meaning the decoded and scaled signals such as speed in kilometers per hour, RPM, temperatures in degrees Celsius, and the like. Now, there can be some exceptions to this rule. As an example, in the heavy-duty world, J1939 is a standardized protocol that is used by most manufacturers, and as a result, you will be able to decode a large share of the data that you find on an average truck if you buy a J1939 DPC file. And in a similar way, if you have your own car, and if we're talking a non-electric car, you can typically get some data through OBD2 requests, essentially asking the car to provide you with speed, RPM, and some other parameters. But what you're getting is essentially the discount version of what is available on the CAN bus. You are only getting a light subset, in this case, through OBD2. So if you want specific signals, or if you want the more rich data that is being communicated in your car, you essentially need to reverse engineer that information. And that's the exercise that we'll go through today. And this is relevant not only if you are a car enthusiast, but also in, you can say, the professional world, if you are an aftermarket provider of, let's say, telematic services in a mixed heavy-duty vehicle fleet, then you often need to do at least some reverse engineering in order to complete a DPC file and get the information you need in order to solve the use case you need. The problem with doing reverse engineering in practice the classical way is that you essentially need to be a bit like a tank from the Matrix. You need to use tools like SavvyCAN, and you need to do a lot of, you can say, ad hoc human analysis on the fly, where you're looking at bits of the CAN data bytes that are flipping. You try to correlate this versus what you're seeing in the real world, and if you get really good at it, then you are able to, in many cases, reverse engineer at least some CAN signals, but it can take hours to do so. And in my opinion, it is only really possible if you have some serious expertise within the field. So what I wanted to do was essentially to check, are we able to leverage AI in order to make the CAN bus reverse engineering exercise more easy and more accessible to non-technical users. And basically the way I went around this was to build a Claude Code skill, and I'll explain a bit more in a moment. And I tested this on a diverse set of CAN signals and real-world practical exercises in order to iterate towards something that actually works really well. Now, I'm not trying to push my particular skill. It's 100% open source. You can go and pull it, and you can use it also quite easily with other tools than the CANsub. My goal is more to showcase a workflow that I think works really well. And if you want to use the skill, that's fine, but you can also build it from scratch yourself. And let me explain essentially how I went around building this particular skill. So, first of all, if you're not familiar with Claude Code, I strongly recommend just watching some quick videos on this on YouTube. But the gist of it is that it's a bit like a ChatGPT that you may have tried in your browser, but where it has access to all of the files, folders, Python scripts and the like, and can run scripts on your PC. So it's a bit like running a chatbot locally where it has access to tools. And if you're using something like Claude Code frequently for the same type of workflow, then it can be a good idea to create what is called a skill for Claude. So a skill is essentially just a folder consisting of some files and potentially some scripts. And in our particular case, the skill I built contains some instructions for Claude that tells it when are you supposed to use this skill, what are the workflows that are supported within this skill, and step by step how do you go through it, specifically in this case reverse engineering some arbitrary CAN bus signal that the user is interested in. And in order to enable Claude to understand stuff about reverse engineering, I have provided it with some reference articles, but I have also provided it with details on our CANsub.2, so the product I use for this, as well as documentation on the Python-CAN integration for the CANsub.2, so that Claude will know what are the things it can do. For example, if it needs to do some quick scripting that goes beyond what is available in the skill. But for the core workflows that are being used in this skill, Claude has also built a number of Python scripts that use the Python-CAN integration in order to access the CAN bus, for example, through the CANsub.2, but also to analyze CAN bus data in the form of CSV files, as well as build DBC files as the final output from the exercise. And this is critical because Claude will not have a chance at reverse engineering anything if it just gets, for example, a raw CAN trace that might consist of, let's say, millions of CAN frames. That is not a good way for a chatbot to operate. Instead, you want to provide it with a method of getting the insightful results and the statistical results out of various analysis, and only focus on that to keep the context window as minimal as possible for the chatbot. It can be, you can say, interesting or intuitive that you could essentially just pass to Claude the full raw CAN trace from your vehicle, ask it to, reverse engineer everything, or even reverse engineer, specifically speed, and then let the AI do some magic. And unfortunately, that's not how the real world works, at least today. So in order for Claude Code to have a chance at actually successfully reverse engineering the signal you're interested in, you have to tell it what that signal looks like. And since you don't have the decoding rules for the CAN bus, you need to provide a reference signal that closely correlates with the signal that you are targeting. So if we take speed as an example, the ideal reference signal for a proprietary speed signal in a car, for example, would be if you have access to getting the OBD2 based speed. And that is because, as I explained, OBD2 is a standardized protocol across cars. It is accessible in most modern non-electric cars, and that means you can use a tool like the CANsub.2 to request speed from the car, let's say every 300 milliseconds. And you then have this reference signal in raw form in the same CSV file as you have your proprietary raw CAN bus data. And these signals will be more or less perfectly correlated, which makes it much easier for Claude to detect what is the related underlying speed signal. If you don't have a CAN-based signal, you can also use a vision-based signal. So a good example is, again, if your car shows the vehicle speed on the car's dashboard in a digital form, then you can record this with your iPhone or with a webcam, and then the skill has support for using Python to turn this video into, you can say, a time series dataset, pretty much giving you the exact same result as you have when you use a CAN-based signal from OBD2, a GPS to CAN module, or something similar. So nearly a perfect reference signal. If these options are not available, as a last resort, the skill also supports that you can use human input, and this can, for example, be relevant if you have no digital representation of the signal, but you are, as a human, able to monitor it visually. For example, that can be me turning some gauge on a sensor to CAN module, or it could be something you can observe in your car, but where you are not able to record it and turn it into digital data. So I will show you how you do that through a small app in the tool as well. But once you give Claude the reference data, as well as the raw CAN bus data, it goes through a number of analysis steps, doing statistical analysis, serving the CAN bus data surfacing what are the correlated target potential candidates for your signal. And based on this and doing a number of different steps that I'll cover in a moment, it is able to get to a conclusion in almost all of the cases that I have tested where it has detected the relevant underlying proprietary signal correctly, and it will then create a DBC file based on this result that you can directly use to decode your data in tools like webCAN. Now, in this skill here, I've built it around our CANsub.2 CAN bus interface, and you don't have to use that for this particular exercise. You can use any CAN bus interface that integrates with PythonCAN, and you could even go beyond this if you wanted to redo some of the scripts here. Again, my goal here is to showcase this workflow. If you want to use a different tool, you can definitely do that. And I would also, to be brutally honest, say that the CANsub.2 is perhaps a bit overspec'd for some reverse engineering use cases. This is a professional grade tool that is targeting primarily engineers working at OEMs in the automotive industry, where it is critical that the tool has a lot of professional grade features and functionalities. With that said, I know we have a lot of users within the CAN bus reverse engineering space, and we have had that on some of our older devices, and I would say the CANsub.2 is perfect for CAN bus reverse engineering for a number of reasons. One of the reasons is the fact that the device has this small LCD display on the backside, and when you are connected to your CAN bus with the CANsub.2, you will be able to monitor things like the frames per second, the bus load. Are you actively in silent mode right now? Are there error frames on the CAN bus? What kind of bit rate are you using? And a lot of stuff like that. And this is useful because when Claude is doing its thing, you don't really have much transparency into what's actually happening under the hood through the terminal, in my opinion. And here I find it to be really, really nice to be able to follow along on the LCD of the CANsub. The second big thing that the CANsub facilitates is the tool called webCAN. So this is an optional tool that you can use with the CANsub, along with many other tools. But it is a browser-based GUI tool that you can essentially access by simply entering the URL of your device in your browser. And this opens up webCAN directly with no installation because the tool is actually hosted on the CANsub.2, which is a quite unique combination that makes it really, really practical to use. And you can use this offline in your car. It doesn't require internet connectivity, and it does pretty much everything that you would find in, you can say, similar CAN bus tools. And in fact, it also does a lot of professional grade stuff that you normally only find in paid CAN bus software tools. This includes things like being able to decode live with DBC files, handle transport protocols like J1939, transport protocols, and ISOTP. It also allows you to directly plot and visualize the data that you have recorded within the tool, which is really, really useful when you want to review in real time if your DBC file looks to be valid. And I'll show more about that later. The CANsub.2 also supports silent mode and error frames, which I think are critical features when you are doing CAN bus reverse engineering. In particular, if you're doing it in live and safety critical vehicles, you want to be able to use silent mode during that analysis. And finally, the CANsub.2 supports dual CAN buses. Now, in many cases, this is not necessary because if you are able to get the proprietary CAN bus data along with, for example, OBD2 data through a single connector in the car, then you're in luck. You have a very simple setup, and this would be my starting point for most users to try out. But in many modern cars, the access to the raw proprietary CAN bus data is going to be deliberately blocked by the manufacturer through the OBD2 connector. And that means you are still able to use the OBD2 connector to get your reference signal, and you can do that through, for example, channel 1 of the CANsub.2, but then you need to get access to the proprietary raw CAN bus data from another source. And typically the way you do this is that you take a contactless CAN reader, you snap it onto the CAN high and CAN low wiring harness in your car. Often you need to remove a panel to access this. And now you have the possibility with the CANsub.2 to record both the OBD2 reference signal and the proprietary CAN bus data into the same fully time-sorted trace view, and you can export that CSV from webCAN directly for use by Claude Code. where if you were to record this separately, the whole point would be lost. You essentially need to have these two data sources in a single file in order for Claude to be able to do its thing. If we look a bit more into some of the actual showcases that I also provide in the article, the first showcase I do is very simple. I have recorded with the CANsub.2 some data from a car. This is specifically from a Mercedes E350, where I have some raw proprietary CAN bus data and I have some OBD2 data as my reference signal. And in this case, I actually asked Claude to reverse engineer two signals up front, speed and RPM, and I explained that I have available a CSV file which contains also the OBD2 data it needs. Now in the skill, we have packaged our OBD2 DPC file, and that allows Claude to quickly decode the OBD2 signals from this data, so it has the reference signal it needs to identify speed and RPM from the data. And if you look at the steps I take here, you will see that Claude is doing a lot of work to trawl through the data with the different tools. And it does a couple of things here. It does a survey of the data. So that involves essentially a bit the same steps you might have seen in SavvyCAN and other tools, where you are looking at which bytes and which bits are changing in response to certain information or certain stuff happening in the real world. Claude is doing the same thing across the entire log file to get an idea of what are the patterns of the different CAN IDs and the different payloads in the data here. This serves the purpose of, for example, identifying if some of the CAN IDs are irrelevant to the subsequent analysis, and also if some of the data bytes seem to be, for example, counter signals, checksums, or other types of signals that might disturb the subsequent correlation analysis, but which are not really relevant for the specific analysis or reverse engineering exercise. Once we've done that step, Claude will do a correlation analysis, and in here it will essentially rank different candidate fields. So that will be, byte chunks of the data, and it will try and look at how well these correlate against the reference signal without having to take into account the scale and the offset, because we do not know that information yet. And from this analysis, Claude will typically get a few candidate potential signals, and it can then do the next step, which is a bit search. And here Claude does essentially all of the potential variations of, bit start, bit length, endianness, signed, unsigned, all of that stuff in a lot of iterations. And again, the idea here is to correlate and identify which of these combinations will give the best match against the reference signal that it is provided. Once it has done this exercise, Claude should have essentially the relevant bits, you can say, of the signal that we're trying to reverse engineer. And now it's just a matter of doing more of a statistical exercise to identify what is the scale factor that will make this graph that we can plot from these extracted bits look like the graph of the decoded signal we're matching up against. And once the scale has been identified, the second step is to find the offset, so that you have all of the information that is required for a CAN signal in order to create a DPC file of this. And once Claude is done with that, it will create a DPC file for this particular signal. And as you will see from the video here, Claude does this in a nice way, where it creates a decoding output folder, it creates a subfolder for the application based on the context I provide, and it also does a subfolder below that for the specific signals that we are reverse engineering. And this is where Claude will put the DPC file. It will also put the plot showing how well this correlates against the reference signal. And it will also put some of these analysis plots, mainly for us to understand what is actually going on under the hood. But in some cases, this can also be useful to guide Claude in the right direction if it goes off track in the analysis. So as was expected in this case, Claude was able to reverse engineer speed and RPM without any issues, because it had more or less a perfect reference signal. But this may seem trivial, but this is a really, really powerful way of achieving this, and not something that a non-technical person would otherwise be able to do, even if they have the reference signal available. Now, to take it one step further, I also did a test in a car, basically an old Opel Astra, where I get access to the car. I set up the CANsub to request some OBD2 speed information to be sure that I have a reference signal for my subsequent analysis, but the goal here is to essentially showcase what would I do if no OBD2 data was available. For example, in an electric car, you often don't have the luxury of OBD2 data, and therefore you need to look at what is the second best thing that you have. And in my opinion, that is the OCR method, where you record a digital value of the signal from your car's dashboard, for example, with an iPhone, or better, I would say, with a webcam that is synchronized to your PC time, and thereby the CANsub's time. And you can essentially record this data while you are driving around. And in my experience, you want to do this, if possible, at later in the day, so there's not too much sunlight. And you would also want to do it in a way where the webcam is quite stably positioned in order to minimize the drift around. But I did the worst case scenario, and it turns out that Claude and the script utilities are able to handle this pretty much perfectly well. And as evident from the video here, one of the steps in this workflow is that you get your video and you get a signal, or you get essentially Claude's and the script's output time series, and you get sort of the current value at the frame you are at in the video, so you can quickly review if your video turned into the expected time series data and how many errors you had in case you want to go back and redo it. But typically you can get quite far with quite simple means with this. Again, now Claude has a reference signal available, and it is able to run through the exact same analysis as in the OBD2 case and reverse engineer the proprietary speed. And in this case, I also recorded the OBD2 speed just as a proof to show that it was in fact the correct speed we got, but Claude of course did not have access to the OBD2 speed in this particular exercise here. Now let's try something that is a bit harder, which is to say, what do we do if we don't have such a perfect reference signal? And to showcase this, I'm essentially testing with the CANsub.2 and a module we have, a sensor to CAN module called CAN input. The CAN input is able to produce CAN frames based on measurements of voltage in the 0 to 10 volt range. So for this particular exercise, I take my CAN input, and we have a small potentiometer PCB board which has 8 gauges that you can turn with like a small tool in order to translate that into a millivolt output, which by the CAN input gets translated into a CAN frame and some CAN signals. Now I know what the true DPC file is for the CAN input, but of course I don't tell Claude that. And I think it's fairly to be expected that Claude did not find this as part of its training data. It is a bit niche. So what I do in this exercise is to say, can I essentially move around this gauge in real time with my right hand, while at the same time with my left hand I use the skills built-in web app to move a slider up and down. So the way this works is that I have told Claude a bit of context up front, as you can see as in my prompt here, and this allows Claude to start up this web app with the settings already matching the context I provided, so I don't have to fill in any fields. Claude has taken care of that. And then it will ask me to do some captures in real time with the CANsub.2, where it records data while I am doing something with the reference signal in real time. So I would essentially start the capture, and then the first pass is to do this time slider, or not a time slider, but this slider from 0 to 100%, representing essentially me moving this gauge from 0 to 100%. And this is hard, as you will see from the comparison graph. It is hard to match these exactly, so I do it as best as possible, and I do it a few times from 0 to 100 and back to 0, and try as much as possible to follow along with both of my hands. But in order to get a more precise second pass of this, the skill also supports that you can set in some sample observations at different values, you can say, of the reference signal. So in my example, this corresponds to setting the gauge to 0% and then hitting the 0% sampling. Then I will see from the chart in the app that it samples for these 2 seconds. Then I can move the gauge to the next point, maybe that's 50%, and again I can sample for 2 seconds, etc. And I can do this a number of times, and that gives a bit of an anchor for the different signal values that is less dependent on my poor and noisy human input that I'm able to provide in the first pass. So when I have provided this, I essentially tell Claude that now we're done, please proceed, and then Claude goes through the next steps as before. And again, in this case, I think this is probably one of the ones where I'm more surprised that it is able to manage this, but Claude is able to take even this very, very noisy reference signal and manage to decode the correct decoding rules for the CANbot input based on this. And something it also does that is quite nice in the context is that it often discovers that maybe there are separate signals that are encoded in the same way. So in this example with the CANbot input, I'm asking it to reverse engineer the first gauge, but I did tell it that there are 8. So based on the decoding rules it found for the first gauge, it sort of figures out that probably the next gauge values are also encoded in these and these data bytes. And it will then ask you, do you want to proceed to try and reverse engineer these? And I essentially tell Claude, hey, based on your hypothesis, try and create the full DBC file, basically do the exercise for all of the remaining gauges, but don't await my input for it, just build the combined DBC, and it will do so. And then I will take this DBC file, load it into the webCAN tool, and then I can sit and move the gauges for all of the 8 gauges and verify that the decoding rules match. I'm essentially seeing on my screen when I plot this data exactly what I'm doing physically in the real world. So I would say this is a useful exercise if you are busy and want to just get, a couple of extra signals down, and then you prefer to verify the data rather than go through the manual exercise each time. Now, if you want to try this yourself, you can get the CANsub.2. As mentioned, I would get the OBD2 DB9 adapter to start with, and then you can try if you can, get the data from your car, the proprietary CAN data, through the OBD2 connector itself. If so, that's the simplest solution. If not, then you can get the contactless CAN reader we have, and maybe like a cigarette receptacle adapter we provide for powering this, and then you can try the contactless method. I just would stress this does require a bit of digging through your car, removing a panel here and there in order to find out where the CAN high and CAN low is. So this is a bit more for the experts or the technical users that want to do this. But if you are patient, you can also do it even without prior experience. If you want to just try out the skill right away without our devices, you can also get the test data that I use for some of these showcases. So you can download that and you can use actually the full workflow from Showcase 1 and Showcase 2 just with that data. My video that I recorded for the second showcase is also included in there. The skill itself is available on GitHub, and you can find the link in the description, and you just go to the GitHub page and you can essentially clone or download the zip file with the skill, put it into some folder, and then you want to open up Claude Code from that folder. And in the README on the GitHub page, I describe some of the details like how do you set up Claude Code, how do you get the exact same setup as I have in Visual Studio Code with the plugin, which I like. So you can go there and find the various steps inside. My estimate is that setting this up will take around 10 minutes, so definitely try it out with the sample data. But to summarize, I did many more tests than what I showcase here, and I would say across all of the tests, I'm pretty much blown away by how effective this workflow is. Pretty much all of the signals that were available in the proprietary CAN data and where I did have a reference signal that was clean, it was pretty much 100% success. There are some cases where Claude goes off on a tangent and you need to help it a bit, but I would say even in these cases, it's often able, based on, logical analysis, to say, hey, this correlation is not as good as expected, that's probably not the right path, let me review again, and it goes back and forth, and actually even in these cases ends up with the right signal, which is equally impressive as these single shot showcases that I showed you before. I think the really big impact here is that when I tell our users that yes, you can reverse engineer CAN bus data using the classic methodology, I typically also say that you should expect to spend 2 to 6 hours per CAN signal that you are reverse engineering. And I honestly think that is the realistic time it takes for somebody that does not have multiple years of experience within this field. With the skill here and with the methodology, I would say that the exercise actually takes closer to 5 to 10 minutes per CAN signal, with most of this being me drinking coffee in the background while Claude is running through all of the steps. Of course, you need to record the data, but again, using something like the CANsub.2, you can very quickly get these the raw CAN data and the reference signals. So that is also not a huge exercise. But again, just like the classic methodology, this is not some magic AI overlord doing hocus pocus, so you cannot simply provide it the raw CAN data without a reference signal. That is going to be useless for Claude. You are limited still to what signals you are able to get a clean reference for. But definitely hope you found this useful and interesting, and if you did, make sure to like and subscribe the video. But more importantly, I really hope you'll share this in your community, and you're always welcome to reach out to us if you want to discuss this, if you have suggestions, or if you just have questions about using our products. Thanks for watching, and see you next time on my next video.